All right, I talked a little bit about the bore surface. And I will show you how to do a hone. I just have to remember to do it. Next group that goes through the cylinder line, I'll do that if I can actually break free. All right, so the cylinder. It is honed to a finish. Honed to finish. And it is given to you in a RMS finish. What does RMS stand for? It means that it is measured with, you can either use a profilometer, I think root word being profile-o-meter, or two, surface roughness scale comparator block. I do not have an example of a surface scale comparator block with me, but it's a little leather or fake leather wallet that you open up, and it has a steel in it that has been to each scale, rough to each scale. And so you would literally just go, well, let's see here. That kind of feels like that. It looks like that. And there you go. It's that one right there. I had to write a procedure, which I may or may not get into. Yeah, I will, because it got me in trouble, and it's not funny, but I'll tell you the story because it's a good story. What's that?
Funny now.
Might as well do it now? Nah, I've oversold it now. But anyway, I had to write this procedure, and it involved a surface finish that we had to finish something to, and so that's how I wrote it. Just use a comparator block. So I bought a comparator block, and just hold the two things up. Yep, that's nice and shiny and smooth with no scratches. That's nice and shiny and smooth with no scratches. So there we go. All right, so I honed to about a 45-degree crosshatch. Crosshatch means it goes not only this way, but also this way. And that's important. I've seen people hand hone things. I'll show you how, because that's all we have here is a hone on a drill. And it's not real hard. When we did A65s, they're very, very small bore, comparatively speaking. They're the smallest ones. They wouldn't fit on our hone. So when I did A65s, which you didn't do a whole lot, I had to hone them by hand. And so what I did to get proficient at it is I took a cylinder and I honed it on our nice machine. And then I sat it right next to me. And then I got a A65s, a couple of them, so I could practice. And I would practice what I needed. I figured out, I knew how fast our hone went around, so I would get the drill going about that speed, and then I would just kind of emulate about how fast that went up and down, and I would do it, and I'm like, hey, I'm actually, you can do it. So once you have something you can mimic, you can do it, then you get that kind of muscle memory going, and it's not hard at all. But I've seen people, hone out a cylinder, they'll just put it in there and just, squeeze the trigger, and it goes around like that, and so you have no cross-hatching, you just have circles. And that's not going to work. Or you can go too fast and you get it too steep, and that's not good. So, I don't know, if you get it too steep or too flat, you could, I guess, pump oil or not get enough oil in there or just have problems. I don't know which would do which. I will say that, let me see. I feel like there was an A point there. Oh, well. Too smooth. So what if I didn't get the right RMS? It was just barely crosshatch in there. What would happen if you think I got it too smooth?
Not enough oil.
You got it. Too smooth will not hold enough oil. What if it's too rough?
Too much oil.
How about excessive wear?
Excessive wear.
Yeah, it's really rough. It's really hard on those rings. So
Would that affect compression at all?
What?
Would
Yeah, then it would ultimately affect compression, for sure. So most cylinder wear, Where's most cylinder wear going to happen? Top of the cylinder, as it sits like that.
No.
So
Near the valve.
near the valves. And where does Lycoming have you measuring it? How far away from the valves? It's not near the valves. So most wear is going to be about ½ inch up. That's where most of the wear is, half to 1 inch at the most. So I find it interesting that Lycoming says, no, don't measure it there. Don't look there.
Yeah.
Up a little bit. See, we're fine. Continental's pretty specific about getting down in there. Most cylinder wear is at the head. Due to heat and pressure. Due to heat. A lot of heat up there and a lot of pressure. And then I heard something the other day, listening to a podcast, which I never thought about. I don't know how true it is, but it was the water skiing analogy. It's actually Mike Bush who said it. And he said, well, there's no wear through most of the cylinder because the cylinder is moving quickly and there's a film of oil, and therefore the rings are riding in that oil, much like it would be if you're pulling a water skier. It's moving fast. The water skier is moving fast. They glide on top of the water. So the rings, therefore, are gliding on top of the oil. Well, when you get down near the head, it slows down and stops. That's like if you're pulling the water. Do you guys water ski? I do. Yeah, so you slow the boat down, what happens to the water skier? They start sinking. So the rings start slowing down, and therefore it loses that hydrodynamic surface, and it falls towards the cylinder and then scrapes the cylinder till it turns around and goes the other way.
If that was true.
I know. As I'm telling the story, I'm thinking, hey, wait a minute. And then I can see him start to laugh. I'm like, Mike's got it. If that were true, then it would do it on both ends. But it doesn't.
Another way maybe to look at it is that you're going to get very little oil near the top ring
Yeah.
because of the wiping action of the lower ring.
Yeah. I'm sure there could be a little bit of truth to that. I'm not going to say it's totally false, but it definitely has to be in play with something else. Either there's just so much more oil at the other end, or I think the heat and the pressure have a lot to do with it. Something I don't have in my notes that I did hear, which is interesting. Normally I go into compression tests in great depth, but I don't want to anymore because Larry does it, and so he does a fantastic job. So there's no need for me to do it, and he's going to do it anyway. So I'll talk about something else. But in all my years of working on aircraft, this is something else I heard on the AOP podcast. I had never heard of this, and I'm just going to throw it out there. Maybe you car guys have heard it, but we do a compression test, and I showed you a compression test, and so we're putting air in, and we're measuring how much air stays in as to how much leaks out, and we're testing leakage across the valves and the rings, and in theory, if there was a crack somewhere through that, but otherwise it's valves and rings. And Continental and Lycoming have a very different view on how you go about doing this. Lycoming is more about higher numbers, and they match what AC 4313 says, where you're getting into 60 over 80 isn't really that good, and you got to make sure that you're within so many pounds of the one next to it and across from it and the other ones. Where Continental came up with this master orifice thing, where you take your tool and you turn on the master orifice and you just see what the leakage is out of this tool. It came from the days where they actually had a thing you plugged into the end of your compression tester, and it's just whatever that leaked is. You put your gauge on 80, whatever that leaked was your standard. Well, it's usually about 38. And so you do a master orifice reading, and Continental says, well, as long as it's better than the master orifice, we don't care. For the most part. So you can have a cylinder at 38 over, 80. As we're at Lycoming, you'd be pulling the cylinder. Continental's like, fine. How'd the borescope look? Borescope look fine? You're good. and Lycoming's more about what are the absolute numbers. So it's just kind of funny how they're so very different in what they do. And again, there's probably this really great point I was going to make about that, but it's just they're different. And I think that has a lot to do with just how the cylinders operate. I tend to notice a lot more cylinder wear up at the head on Continentals than I did on Lycomings. So anyway, most cylinder, there we go. Let's talk about the cylinder head now, which is B way out here. So that'd be cylinder head, which is the aluminum part, not the whole thing. So when you say cylinder head, I guess that's one of the few times I correct people, because I'm like, well, do you mean the whole thing or literally the head? I want to know. So that is made of aluminum, high strength aluminum alloy. It is attached obviously to the barrel. It is both a shrink fit. Well, you can have a shrink fit, bolted flange. That would be like, I think Franklin's are bolted. Rangers, I think, your antique engines. Bolted flange. Shrink fit would be like it swells on there. I'm not familiar with anything that's just oh yeah, some of them had sleeves that would go in. So that'd be like a shrink fit, a sleeve would go in. Who did that? Lycoming did that on 235s, and they did not work. They had to take them off. Or threaded, and that's the most common. It's kind of a shrink fit threaded, if you will. That thread that's done at high temps, around 600 degrees. And that's the most common method. Yeah, we'll say about 650. Because these cylinders are going to run around 400, 450 degrees anyway, so you can't have them coming apart. They will come apart. Let's see. Has a lot of parts up in the head. So contains. Well, we can start with the spark plug boss. Boss is because aircraft have 2 spark plugs, all of them. And those spark plug bosses will either be 14 millimeter, which was very rare in aircraft. I think, again, Franklin is the only one I know that ever did that, or 18 millimeter. And isn't it weird that even our World War II engines were using millimeter spark plugs?
No, because they were built in France.
Yeah.
That's how most engines came from overseas.
Yeah, but they built them with standard hardware, but kept the metric spark plugs. So all of the spark plug bosses will have an insert. It's either a bronze bushing, or it's going to be helicoil. And everybody in here knows what a helicoil is, correct?
Mm-hmm.
Oh, there. I got lucky. This one has the brass bushing in there. And every now and then you'll get a spark plug will go in there. It'll seize up in these bushings, and when you pull it out, the bushing comes with you.
Is that the only time they would helicoil it? Is if you
No.
pull bushing out with it, or?
God, why do I want to say that's not these are left-handed thread? I've changed a bunch of them. It's been so long. I thought it was left-handed thread. You can see a little pin. You actually drill an 1/8 hole and just this way you see it better. Drill an 1/8 hole and then you hammer in an 1/8 brass plug into it, and that's what keeps it locked. But I want to say they were left-hand thread for some reason. I don't know why. They came this way from the factory, and if this is what was in there, that's what goes back in. Then they changed it, so all newer cylinders are they come from the factory at the helicoil. So if the helicoil gets messed up, pull it out, put another helicoil. Not a big deal. We obviously have the valve guides.
Did they put that in just as a reinforcement?
Yes.
or-
Yep. Valve guides. We have an intake valve guide and an exhaust valve guide. Almost always the exhaust valve is larger. So valve guides, exhaust is larger. And the intake is smaller. Most of the time. Big bore Continentals are about the same size. Only changed when worn. Because well, my shop, if we pulled one out, we always went to the next size up. Because you pull a little metal coming out, you never wanted to risk having a guide work itself loose while it's in operation. I've seen it happen. I think Larry talks way more about this, so I'll let him do it. But Lycomings are prone to a thing called morning sickness. And, well, that's the symptom. They're prone to a thing called valve sticking, where especially the exhaust valve sticks inside of the guide. And we call it, the engine has morning sickness because what happens is you go out to start up your engine, and because Lycomings tend to be 4 cylinders more often than Continentals, you really notice it on a 4-cylinder. So you start up your engine, it runs really rough. And that's because it's running on 2 or 3 cylinders. You got 1 cylinder where the valve is either just really moving slow in the guide, I mean way slower than it should. You know, the rocker arm forces it open and opens, and it's like the springs take a little while before it starts pulling it back up. And as the aircraft, the cylinder starts heating up, that space starts to get a little bit better, and suddenly it's free. It's like, oh, okay, there you go. It's fine now. Problem solved. No, it's giving you warning. It's about ready to fail on you is what that means. And what happens is the oil gets in between the valve and the guide, and it cokes. All right, that's that varnishy stuff, and it cokes and it sticks. So with Lycomings, you are supposed to it's like 500 hours. It depends on the airplane. Like helicopters are really short interval, but like 400 or 500 hours, you're supposed to drop the valve out and ream the guide. Well, you're not really reaming the guide. You're reaming the coking, oil coking out of it, and then putting the valve guide or the valve back in it. So you got to watch for that. But yeah, we only change them when they're worn out. But we do have to deal with the valve sticking issues. Let's see.
So with that, to ream those guides, does that mean you gotta pull the cylinder?
No. If you notice out, well, you guys are busy, but if you walk out into the lab, there's a procedure that Larry does with your class out there where he teaches you how to do that. So you shove a rope down in here, bring the piston up on the top dead center. That rope pushes on the valve, so the valves are now locked into place. Use a valve spring tool, just like you did in class. Take out the valve springs, keepers, all that. Take that off. Take out the rope. Take the valve. Pink. Push it right down inside the cylinder. Now it's down inside there. Then you ream out the guide, and unfortunately, you get garbage in there and stuff. And hopefully flush it out best you can, but it goes in there. And then when you're all done, you use a little mechanical pliers, little mechanical fingers through the spark plug hole, and you kind of hold it, and you put a magnet through the guide, till it holds it, and you pull it out, and once it's out, put the rope back in and put it all back together. So, but we only change them when they're worn, which I will show you how to do. We have the valve guides, we have the valve seats. If I got a cylinder in my shop for repair, it was 90 to 100% of the time I'd change out an exhaust guide. They just wear. They wear rapidly. And by the way, they wear down at the head end. They wear this way. Bell mount down at the end. So if you're measuring it, don't pull it up this way. Valve seats, don't change them out very often. You only have three sizes you go. Standard, 10, 20, 30, throw it away. So valve seats we didn't change very often because you can reface them so often. But I changed them enough. Let me see, valve seats. Again, only changed when worn. Most cylinders, man, never saw a seat change. They're fine. We have the rocker arm bosses. these right here. Continental, these small Continentals had an airworthiness directive, do have, on the thickness between how much thickness you have between that bushing and out here, because these were breaking. So there's an airworthiness directive that you have to measure that, and on certain cylinders, every single removal of this has to be MDT'd up here for cracks. And if it doesn't meet the minimum thickness, you have to throw them out. So that's probably why that one's sitting there. That's where we got most of our cylinders here. We have the rocker arm bosses, and you can rebush them. I hate doing it. We have the intake port. Some of the stuff I don't have much to say about it. Certainly nothing to write about. Intake port. So intake port has the fewer amount of fins. And while we're talking about intake ports, there are some companies that do port and polishing, where they have an approval to go in and take out material and smooth it out and increase the flow. They'll flow match the cylinders. They have the same amount of intake flow. Do it on the exhaust side too. Kind of the OEM stance is, why don't you do that? Well, the roughness is good. It helps circulate the air and mix the fuel and air, so we get better fuel-air mixture into the cylinder, and that makes more power. And the people who do the port and polish say, that's a poor excuse. You get bad flow into the cylinder, so you don't get as much fuel and air into the cylinder, so we port and polish it. And then to that, some people say, well, yes, but when you port and polish, you remove material, and now you're more prone to cracking. So I didn't port and polish simply because we just didn't offer it. I'd had no problem with it and still don't. Exhaust port. Have the exhaust port. Has the greatest amount of cooling fins. Oh yeah, I forgot about this. It's fun. So Continental or TCM, big bore, has one spark, has top plug, hope I'm right, top plug, points to exhaust, top plug. Exhausting. So literally one plug is in sideways and it points over towards the exhaust side. It has the smaller diameter valve head. Largest stem, smallest head.
It's TCV on Continental.
Teledyne Continental Motors. TCM? That's TC. Oh, sorry. M. Well, because I was going to write big bore, so I'm thinking ahead. I think that's a yogurt place. TCV. It's ice cream. Okay. Yeah.
Backing up the valve guides, a cheap automotive process would be to mirror guides. Do they do that?
On the inside?
Yeah.
No, definitely not. So, all right, since you brought that up. So Lycoming has this problem with valves sticking. And I take no credit for this. It was just kind of handed down to me as like, this is how we do guides. And oh my gosh, it works so well. I never had anybody come back and complain that one of my guides stuck, ever. And what we did is we had a line boring machine, because some guides actually come pre-reamed. And so you just buy them and you pull out the old ones, you ream out the cylinder to the next size, you heat it back up, you drop in the guide, it's to the size, the valve goes in. Lycoming, we didn't do that. So we had to line bore them. So we had a line boring machine. We'd set it up and you'd actually bore, you'd put the new guide in and it's not the right size, you'd bore the guide. And then we would bore it undersized, like it had to be 0.5. So our reamer was like 0.495. And then we take it to another station that had a small hone in it, just what you'd think of as a hone on a drill. And we would then hone it to .4995. And if you look up the dimensions for new, that's like max new is 4995. It's like the only time we ever did something like that to the max. I think because I think minimum was like 499 something, or actually it was like, I don't know, something like that. Anyway, so I would hone them to this really fine mirror finish to 4995, and we just had absolutely no problems with them. So instead of knurling, we'd go the opposite way, super mirror finish. But the guides that we were getting from other places, and even the factory, there would be scratches and stuff in there. It was like a rough bore, and it was like, yeah, good enough. And so I don't know if that is what caused the problem or not. All right, let's talk about valves. Well, I don't know why I have to write this, but I wrote it so used to open and close ports. Open and close the ports. What are the ports? Exhaust port, intake port. Okay. There we go. Should have looked at this before. So parts of the cylinder. What's this right here? What? Which boss?
The rocker shaft.
Exhaust.
Right here, rocker shaft boss. It's got a little white Teflon plug in there. That's the new style. New. Started doing that about 30 years ago, 40 years ago. So it takes a little bit shorter shaft, and you put Teflon plugs in. That keeps the rocker shaft from wearing a hole and creating metal in the valve cover that goes over top of it. We've got, which port is this? Oh, it says it right there.
It's a calibrated intake port.
Calibrated intake port. Calibrated to what? I don't know. Radiographic control. I have no freaking idea what they're talking about with that. I think they're just making up some words there. Yes, it has some fin width and it has spacing. Anyway, we have, what is this part right here that's pressed in? Valve guide. Let's see here. I don't know, there's not much. Ooh, that's got the nickel carbide. Whose cylinder is this? Titan. Titan is ECI. I don't know how old that is. Probably very old. All right, there is the valves that we're going to talk about. Let me see. Oh yeah, I'm going deep here. Okay. Valves. Let's see. This is going to go terribly bad for me. I'll make a distinctive kind of a right there. Nope, I don't want to do that. So we've got, I'll make a valve. Nope. This is not easy. Yeah, there we go. Okay, we got a valve. I'm making half of it right here. So right down here, we've got the face of the valve. This is the margin. And right here we have the, keep it consistent, the face. That's the head. That's it, go this way. Radius. And that should be straight. Stem. Up at the top. We have the groove. That's the tip. All right, the groove. Well, that's where your keeper goes. That's where your keeper. We've got the stem. Stems are rather interesting, believe it or not. Stem, it could be solid, or it could be sodium filled. As far as I know, TCM does solid and Lycoming does sodium filled valves. This does not take into consideration radials and such like that. Let's see. I wrote a whole bunch of stuff right here, and I'll just read this because it's easier. Let's see. Sodium filled exhaust valves have a hollow head and stem filled with about 60% with sodium. Sodium has an extremely low melting point, about 100 degrees Celsius, and a boiling point of 880 degrees Celsius. In a hard-running engine, the valves are hot enough that the sodium in the head of the valve, that would be right here, down here, the sodium here, vaporizes and travels up the valve stem. Vaporized travels to the cooler stem where it condenses back to liquid. There we go, drops. Liquid again. This phase transition from liquid to gas absorbs a lot of heat, and the condensation dumps the heat in the stem where the larger metal-to-metal contact between the valve, stem, and guide transfers the heat to the cooling system. Without this heat pipe effect, what does that seem like to you? It's like more like a rainforest thing going on right there. So you got the internal rainforest. Let's see. Without the heat pipe effect, vastly more heat would have to be transferred through the valve seat. Too much heat through the valve seat, and you get a burned valve. All right. So let's back up a little bit. Let's talk about some critical theory here. Oops. I want this one. This one. There we go. Go backwards. Let's look at this picture up here, and we'll talk about what's happening here. So this head gets really hot, right? So when it opens up, this is the exhaust valve. First we got all this hot gas down here. Then it opens up, and then the hot gas flows through here and on out. And so it's running really hot. Let's take a look at how hot it is. I know I got a picture. There we go. So this represents how hot a valve is running. So we've got the dashed line, which I believe is sodium, and the solid stem is this color right here. And so we can see this area right here is running somewhere between 1,000 to 1,400 degrees Fahrenheit. So if it's a sodium cooled, it's going to be around 1,000 degrees. If it's a solid stem, they're saying it's going to run about 1,450 degrees. That is relatively hot. Now, if we look at how the temperature of the stem right here, it's going to range somewhere between, well, this would be right here, we'll call it 800 degrees upwards to this area right here. We'll call that 1050 degrees. And if it's a solid one, right about here, it's going to be running over 1,200 degrees. So that's really hot. And oil cokes at, I forget the number. It seems like it's less than 1,000. Let me see if I can figure out, where does oil coke at? Let me see. I know it's right here. Synthetic. Oh, there we go. I was right. 572 degrees Fahrenheit, 300 degrees Celsius. So 300 C or 575 F. Close enough. Is where oil cokes. So if your oil cokes 300 degrees up, so we're dealing with Fahrenheit, so we'll go 575. So anytime we reach over 575, our oil is going to coke. We're going to get that coking, which is going to cause valve sticking. That happens all over the place. Now the oil does have to sit there. It takes a period of time. So as long as it's flowing, that's fine, but that's a whole other problem. So here we have this valve is very, very hot. So what are we going to do to cool the valve? How do we keep it cool? Well, it's got to have heat transfer from the valve to the head and then out to the cooling fins. Well, where does that happen? I don't know. Yeah. I would love to know myself. Okay, it's going to happen in basically two places. Heat transfer happens here, where there is some space, by the way, and right here. Well, all the way around, of course, but that's it. And whenever this valve is off of its seat, it loses this spot right here. So it's got to come back to its seat in order to transfer heat out this way. Look, it's already cracked right there. So the longer it's off its seat, the less cooling it's going to get. So problem there. And we're going to get transfer right through here. Oh, again, I keep like losing all these points. Like, oh, I'm going to make this great point. No, I guess I'm just talking about where it transfers. I guess that can translate into this right here is where it seats. So if this seating surface, the seat, against the seat, is where we have cooling, then wouldn't it make sense to have it really fat? Like the more contact area, the better it would be. Well, the problem is the more contact area we create, the less pressure there is between the valve and the seat. So if you get a little turd in there, that's an industry term, a clinker, then there's not enough pressure to break it out, and then that little piece of lead or something that we get, carbon, can actually hold the valve open so it doesn't seat at all. And that's really bad. So there's this happy medium between the seat's got to be small enough to create enough pressure to break through something and also wide enough to give you some sort of heat transfer out of the valve. So we have all these things in play. Let me see. Is there anything else I got to say? Oh, yeah. Okay. So we got the, go back to here. Groove. I got the stem. Let me see. Yep. Sodium cooled. Apparently, you're not supposed to cut open a valve that's sodium cooled to see what the sodium looks like. I don't know. I've never tried it. We have the, I said radius. I should call it neck. The radius is the neck. I will confess that I didn't do this ever, but one of the way, I think it's a Q&A question, how do you tell if an exhaust or a valve has stretched, gotten longer? And in theory it would do that because you're heating it up so much in this area down here where it's radiused and the springs are slamming it closed, so it could stretch. And how do you find stretch? Well, you use a radius gauge, and this radius should be a certain radius. And if it's not, then it's been stretched. Honestly, what I did is you're only allowed up to 2,000ths wear on these. I would just do a micrometer reading right here. And because it doesn't wear there, it doesn't touch anything ever. So it never wears right there. So just take a measurement there, run it down, run it down, run it down, run it down. And if you exceed more than 2,000ths, or if I hit 1.5, boom, valve is gone. So it was pretty rare to reuse an exhaust valve. So once you had a problem, just buy a new one. They're only a couple, $300. No need, a lot of them. Let's see, we got the neck, the head right there. Okay, different types of heads. Different types of heads. We have the flathead, semi-tulip, tulip, and mushroom. When would it be really important to know exactly what kind of valve you have and the name for it? What's that? Probably never.
When you figuring out what kind of.
I think I was a pretty damn good cylinder mechanic, and I'm like, I'm like, oh, that's definitely that one. So, but I'm pretty good at doing it this way. That is a mushroom. You know how you can tell? 'Cause it matches the picture right there. Almost precise, too. Mushroom.
Semi-tulip or not tulip?
Probably a tulip. And then I don't have a semi-tulip. And then flat. Most of the ones we use are flat. You know what they don't talk about? Venturi seats and stuff. That's a whole other thing. That you actually deal with. All right, so different types of heads. You can write those down. Flathead, because I'm not going to write them real. I could, because, you know. If I don't write it, then you don't write it. So head, flathead, the semi-tulip, the tulip, and the mushroom. Most modern engines are the flathead or just a little semi-tulip to them. Margin. Margin's a big deal. You're supposed to measure that. And if it's too thin, if it gets too thin, we call that a feather edge. You get too thin in a feather edge, in other words, you're going to start shaving with it. It gets hot and it gets a little glowy. And if it starts to glow red, we get pre-ignition. Pre-ignition leads to detonation. Detonation leads to catastrophic failure. So we get pre-ignition and burned valves. That is bad. The tip. Tip is often hardened. Stellite hardened. I don't know how to spell that. It's probably not how you spell it. S-T-E-L-I-T. I think that's definitely wrong. Stellite. Oh, this one's beautiful. You can see it just change. You probably are seeing. You see it change color. It's a stellite hardening. It's really hard. Let's see. I guess I do mention that. Okay, I want to make sure I mention that. Exhaust valve, let's see. Different types of head. We got our exhaust valve. Oh, the tip fell out. Again. Uh-oh. That's why I can't have nice things. Somebody happens to see a little tip laying around.
Little silver thing. Ready.
All right. Exhaust valve. Let's see. I think we can condense some of this. I don't need to say runs very hot, or do I? Runs hot. So I'll just write this. Temp up to 1400 degrees Fahrenheit. We already talked about sodium cooled versus solid. Green means stop. You heard me say that. The other class challenged me on that one. So green means stop. So green is a burned valve. Let's just go to that. There we go. Right there, green. Green is bad, and you got a crack right there. Green means stop, says it right there. Somewhere here, there it is. Burned pizzas are okay. So burned pizza looking stuff is bad. That's green, that's gonna burn. So by the time it turns green, you are in trouble. So no green, green is bad. Green means stop. Green is a burn valve, and let's see, oil cokes. 575 degrees Fahrenheit or 300 Celsius, which leads to valve sticking, which I covered. Coke builds up and pushes the valve to one. Oh yeah, it does. It tends to build up on one side. It sort of pushes the valve over which causes problems in how the valve runs, decreases the clearance until there's no more clearance left. We talked about sodium filled, Stellite face, Stellite, S-T-E-L-L-I-T-E. I was kind of close. Let me see. Which has the largest stem, intake or exhaust? Okay. Which has the largest face, intake or exhaust? Okay, so smallest. Or I should say head, not face. All right. At one point in time, going way back, all valves had a 45-degree face. Right here. It was all 45. This is 45, the seat was 45, and 45 together. And then at some point, they changed the intake valves to 30 degrees and left the exhaust at 45. So exhaust is still 45. So exhaust has a 45-degree seat. And I believe the reason why is because a 30-degree seat provided more volumetric efficiency of the air coming in. Well, it would be great to have the air going out nice, but a 45-degree seat allows for more pressure to break up any carbon deposits that might get into the seat and keep it from seating down all the way, which would then lead to a burnt valve. So more pressure cuts carbon. And a little bit more seating surface. And I think that's all I've got time for today.